Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you have links to online seminars and study manuals for exams P, FM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible, at least tax-deductible to the extent allowed by law, donation to support our students, please go to smarturl.it/help-ISU actuary. Here's a problem for today for exam P on probability. X and Y are independent and both uniformly distributed from 0 to 20. Find the probability density function of Z equal to 25x minus 10y. And there are 5 answer choices, but I only showed you 4 because they won't fit on one page. So the first one is f sub z of z equal to 1.5, where non-zero. F sub z, b is f sub z of z with a stepwise formula, 200 minus z over 100,000 for z between negative 200 and 0, 1 over 300 for z between 0 and 300, and 500 plus z over 100,000 for z between 300 and 500. C is f sub z of z equal to 1 over 200 when non-zero. D is f sub z of z equals 200 times e to the minus 1 over 200z for z greater than 0 and 0 otherwise. And answer E is another stepwise formula, f sub z of z equal to 200 plus z over 100,000 for z between negative 200 and 0, 1 over 500 for z between 0 and 300, and 500 minus z over 100,000 for z between 300 and 500. And here's the solution. This problem can be solved in a simplified way, but we will discuss 3 possible solutions in a long drawn-out fashion in order to fully explain possible approaches for such problems involving sums or differences of random variables. To begin with, note that the following, that f sub x of x is 1 over 20 for x between 0 and 20 and 0 otherwise, and f sub y of y is 1 over 20 for y between 0 and 20 and 0 otherwise, and the joint density of xy, f sub xy of xy, is the product of the two because they're independent, so it's 1 over 400 for x between 0 and 20 and y between 0 and 20 and 0 otherwise. And as I said, there are actually 3 possible approaches to solving this, the multivariate transformation approach, the convolution approach, and the CDF technique approach. You should know all of them for exam P, exam P or exam 1, P for Society of Actuaries and Casualty Actuarial Society calls it course 1. So I will show you all 3. So here is the multivariate transformation approach. We consider a transformation which involves the z random variable that we want the density of. Z is 25x minus 10y, and let's just take y to be 10y. I'm sorry, w to be equal to 10y. So that wz is a transformation of x and y, phi of x and y equal to 10y and 25x minus 10y. And the inverse of it is what we get when we solve these as equations for x and y. So if w is equal to 10y, then y is equal to w over 10. And then if that's the case, then z is equal to 25x minus 10y, and 10y well, that's equal to w, so 25x is equal to w plus z, and then x is equal to w plus z over 25. So the inverse function is w plus z over 25 and w over 10. And you might ask here, how do I know that I'm supposed to pick w equal to 10y? Well, you're not supposed to pick anything specifically. The objective is to find the second function of x and y such that you'll be able to find the inverse of the transformation, so obtained relatively easily. There is no unique prescribed answer. You just have to work with something that lets you work with it. For example, w equal to y would do the job. And w equal to 25x plus 10y would do the job, as long as you can find an inverse. Well, of course, you can't make w equal to z, but otherwise, as long as you can solve the equations, or you can find the inverse through solving a system of linear equations, which means that you have to pick something that would produce a system of equations that has a unique solution, and then, of course, that means that the matrix of the equation has to have a non-zero determinant. But simple will do. I thought that 10y was simple enough. The key point is that you must be able to find phi inverse and then find the determinant of its derivative, the Jacobian. So let us find the derivative now. We're going to work with lowercase variable, but what we have basically is that x is equal to w plus z over 25 and y is equal to w over 10. So partial of x with respect to w is equal to 1 over 25. Partial derivative of x with respect to z is 1 over 25. Partial derivative of y with respect to w is 1 over 10. And partial derivative of y with respect to z is 0. And the determinant of this is negative 1 over 250. And so that the absolute value of the determinant is 1 over 250. And f sub wz of wz is equal to f sub xy of x that corresponds to wz and y that corresponds to wz times the absolute value of this Jacobian determinant of the matrix of the partial derivatives of the inverse. And that's equal to 1 over 400 times, because the density of xy is of course constant, 1 over 400, times 1 over 250, so that's 1 over 100,000. We also have to figure out the ranges for w and z, the possible ranges of values. As w is equal to 10y and y is between 0 and 20, we have that w is between 0 and 200. Also, as x is between 0 and 20 and x is equal to z plus w over 25, so that 0 is less than z plus w over 25 less than 20. This means that minus w is less than z less than 500 over w, or equivalently, minus z is less than w, which is less than 500 minus z. And graphically, if we draw the wz coordinate system, what we have is that w is between 0 and 200, as you can see, to the right of the vertical axis, up to the level where w is equal to 200, and then w, well, z is greater than minus w, so you see the line there where z is equal to minus w, and we want to be above that line. And then z is less than 500 minus w, and you can see the line there where z is equal to 500 minus w. That's a line with slope negative 1 going through the vertical axis at the point of 500 with a slope negative 1, so that's why you can see that slope from minus w. And so the region marked with dotted lines is where the possible values of w and z are, where the density is positive. The density is positive in that region of this kind of a parallelogram. So now we can figure out the marginal density of z by taking f sub z of z to be the integral over all values of w of f wz of wz dw. And that's the integral from minus z to 200 when z is between negative 200 and 0 of the of 1 over 100,000, which we just calculated as the density. Then for z between 0 and 300, the integral goes from 0 to 200. And then for z between, for z between z between 300 and 500, it goes from 0 to 500 minus z. And in all cases, it's the integral of a constant. So all we need to do is just take the length of each interval and multiply it by 1 over 100,000. So it's 200 plus z over 100,000 for z between negative 200 and 0, 1 over 500 for z between 0 and 300, and 500 minus z over 100,000 for z between 300 and 500, which is answer E. We have completed the solution the first possible way. Here is the second approach, the convolution. So recall that if x and y have a continuous joint distribution and are continuous, then the density of x plus y is f sub x plus y of s equal to the integral from minus infinity to plus infinity of f sub xy of x, s minus x dx. And if x and y are independent, then the joint density is written as a product of the two densities. So this becomes f sub x plus y of s equal to the integral from minus infinity to plus infinity of f sub x of x times f sub y of s minus x dx. In this case, we are adding u equal to 25x, which has the uniform distribution on 0 to 500, and is independent of w equal to minus 10y, which has the uniform distribution on minus 200, 0. The density of u is 1 over 500, where non-zero, and the density of w is 1 over 200, where non-zero. So these are the two random variables whose sum we are considering. Adding them, but I mean that we're taking u plus w, and we will try to find the density of u plus w, u plus v from the principles of taking the convolution of their distribution. So f sub u plus v of s is equal to an integral from minus infinity to plus infinity of f sub u of u times f sub v of s minus u du, and that's the integral for u between 0 and 500 and s minus u between negative 200 and 0. That's where these densities are positive. And the first density is 1 over 500, the second 1 over 200. So we need to figure out that condition. What is the intersection of the interval where u is between 0 and 500 and the interval where u is between s and s plus 200? So when s is when s is less than negative 200, then s plus 200 is less than 0, so there is no intersection of the two. So the intersection starts when s is at least negative 200. And then when s is between negative 200 and 0, this intersection is from 0 to s plus 200. The interval from 0 to s plus 200, and we're taking the integral of 1 over 100,000 du. And of course the answer then is 200 plus s over 100,000. That's for s between negative 200 and 0. When s is between 0 and 300, the intersection is from s to s plus 200, the intersection of the two intervals. One where u is between 0 and 500, and the other one where u is between s and s plus 200. So in this case, the length of the interval where we're taking the integral is 200, and we taking integral of a constant, so we basically multiplying 200 times 1 over 100,000. That's 1 over 500, and that's for s between 0 and 300. And the last one, where s is between 300 and 500, the intersection of the two intervals is the interval from s to 500. We're taking the integral of that interval from s to 500 of 1 over 100,000 du, and this becomes 500 minus s, the length of the interval, divided by 100,000, and that's for s between 300 and 500. And of course that's answer E. Again, the same thing. And now we will just try to figure out the CDF of 25x minus 10y in the third method, the CDF method. Directly. So f sub z of z is the probability that z is less than or equal to z, which is the probability that 25x minus 10y is less than or equal to z. The property can be obtained by simply taking the integral of the joint density of x and y over the region where this happens, where 25x minus 10y is less than or equal to z. The figure below shows the region where the joint density is allowed to play, and the shaded area is where 25x minus 10y is less than or equal to z. So the line is where y is equal to 2.5x minus 0.1z, which is what you get when you solve this for y. And the joint density is positive on the square 0 to 20 times 0 to 20. And we want to be above this line. So we want to be in this shaded area. And we want to take the integral of the joint density over this. Well, the problem is that the position of the line y equals 2.5x minus 0.1z can vary as z varies, and we get different results in different cases. The line crosses the point 20, 0 when z is equal to 500. If z is greater than or equal to 500, then the line does not go through the 20 by 20 square at all, and the property of being above the line is 1. Since the slope of the line is more than 1, the next point where a change occurs is when the line crosses the point 2020, which occurs for z equal to 300. So the value of CDF of z for any z between 300 and 500 is shown is the area shown in this figure, right above the line. That area indicated with dotted lines. The point where the line crosses the x-axis is at xy equal to z over 25 and 0, and the point where it crosses the line x equals 20 is at xy equal to 20 and 50 minus z over 10. The area of the bottom right triangle left out of the calculation of probability is therefore 1/2 times 20 minus z over 25 times 50 minus z over 10, and the corresponding probability is 1/400 times that, so that the probability we're looking for is 1 minus 1/2 times 1/400 is 1/800 times 20 minus z over 25 times 50 minus z over 10. Well, the corresponding density is a derivative, and we take the derivative and we get eventually 500 minus z over 100,000 for z between 300 and 500, and this is the same answer in this range of values of z that we obtained before. The second case starts with z for which the point 2020 is crossed by the line when z is equal to 300. In this case is generally described by this figure. This case ends when the line crosses the origin, so when z is 0. Between z equal to 0 and z equal to 300, the probability we want to find is just the area of the shaded region as a fraction of the area of the 20 by 20 square. The bottom side of the shaded region has length z over 25 from y equal to 0 in the equation of a line, and the top side has length 8 plus z over 25 from y equal to 20 in the equation of a line, so that its area is 20 times 4 plus z over 25, or 80 plus 4/5 z. As a fraction of the entire area, that's f sub z of z equals 80 plus 4 over 5z over 400, so 1/5 plus z over 500, and the derivative of that is 1/500, and this is for z between 0 and 300. And that's a density for those values of z. So again, this is the same answer we had before. And the final case is when the line crosses the y-axis above the origin but below 20. When the line crosses the origin, z equals 0. When the line crosses the y-axis at the point 0, 20, we have z equal to negative 200. In this case, the figure looks like this. When y equals 20, we have x equal to 8 plus z over 25, so that the area of the marked triangle is 1/2 times 8 plus z over 25 times 20 plus z over 10. The 20 by 20 square has the area of 400, so that f sub z of z is that area that we just calculated divided by 400, and that becomes 8 plus z over 25 times 20 plus z over 10 divided by 800, And the density is the derivative of that, so we take the derivative and we get 200 plus z over 100,000 for z between negative 200 and 0. This is again the same formula we obtained before, and answer E again. Please remember, this is copyrighted material. The problem was created by me, and the solution was created by me. All rights reserved. Reproduction in whole or in part without express written permission from the author is strictly prohibited. Good luck in your studies and good luck on the test.